So my name is Sean Heelan, and today I'm going to be talking about heap layout optimization for exploitation. So I used to work as a security researcher at Immunity, doing predominantly exploit development and that sort of thing. And since then, I've moved more towards into trying to automate aspects of reverse engineering, bug finding, and exploitation. So the exploit development process at a very, very high level, I guess you could view as something like this. So we have some means of discovering vulnerabilities, we have some means of figuring out what the program's API is, and then the process of producing an exploit is actually programming, right? So we're using available vulnerability triggers, we're using the standard API, and we're programming the state of the target application in order to move it into a state that's advantageous to us as attackers. What we're going to be looking at today, predominantly focusing on, is this part here. So once we have vulnerability triggers and we know how to interact with the program normally, how do we combine these two things in order to achieve whatever ends that we want? So typically, when we're doing exploit development, we want to build our own API, which is separate from the standard API provided by the program, around these things we call primitives most of the time. So we have read, write, or execute primitives, and what they do is they provide the attacker with the ability to, say, read a particular memory location, write a memory location, or execute code at a particular memory location. And these, along with the standard API, are what we'll typically consider to be the building blocks of an exploit. And how we put together primitives, usually we'll have, say, one or more vulnerability triggers, and we have some means of manipulating the program state, and we'll wrap these up in a nice API, and then we can use this whenever we want to, say, write a memory location or read a memory location. So to give an example, say we have a target program which has this user data type, which is dynamically allocated on the heap. We have this rename function, which contains a pretty obvious buffer overflow over the name buffer associated with a user. And then we have this display function, which reads from the user object a pointer, and then it displays in some way that we assume that the user or the attacker can access that data. And what we want to do is we want to construct a primitive, which is an API that the attacker can use, such that whenever they want to read something from some location in the program's memory, they can call that function and have that data echoed back to them. So what happens if we just trigger the vulnerability? Right? So we just trigger the rename function, we overflow whatever is after the name object, and then we'd call display. Well, it entirely depends on the state that the program's in when we trigger that vulnerability, right? So whatever is directly after the username object is going to be corrupted. That could be an unmapped page, it could be allocator metadata, it could be some other dynamically allocated application data. And sometimes we could get lucky and we could corrupt the thing we actually want to corrupt, and then other times we could corrupt say some pointer that's used, and then we get a segmentation fault or whatever. So if we consider like this thing at the top here to be a representation of the program's heap, so from lower addresses to higher addresses, and we have a user object allocated on the heap, and the name object is about to be allocated. So our goal is we want to position the name buffer immediately prior to the user object, such that when we trigger the vulnerability, the user object gets corrupted. We can control the values of its internal members, so the pointers, and then when we call the display function, we can basically read whatever location we want in memory. So if we simply trigger the allocation of the user object, and let's say these green things are free chunks in memory, the allocator will use whatever process it has for deciding where to put that name object in a buffer that's of the correct size, and it can go anywhere. So for example, it could be placed directly after the user object and adjacent to this unmapped page. Now if we trigger the vulnerability, what's going to happen is we're simply going to end up with the process being killed because the page isn't mapped. However, let's say first of all we fill that buffer somehow. Now we trigger the creation of user object again in this situation. This time the allocator picks the first free page, or sorry, the first free location. Now in this case, it's still not quite what we want because we're still going to corrupt some application data in this location here. So that's still not quite what we want. So if we manage, however, to fill that, now we're left with no more free chunks of the appropriate size. We allocate the user object, we allocate the name object, the name gets placed directly before the user, and now when we trigger the vulnerability, what's going to happen is the user object is going to get corrupted. So in this case, we're going to corrupt the user object with like the OX414141. Now when we call the display function, instead of reading the contents of the name, it's going to read the contents of that address, and everything's fine and we win. So the point here is that simply triggering a vulnerability isn't sufficient in order to achieve our ends. We need to perform this manipulation stage ahead of time to put the application into a state that results in what we want happening. So the final primitive might look something like this. This is going to be a function, say, on the attacker side within their exploit where they have some way of manipulating the heap. Then they allocate the user object, trigger the vulnerability, and call the display function. This is wrapped up in a nice function. They just pass in the address, and now in future, anytime they want to read some address in the target application, they'll call this function. And it's a similar idea behind like normal programming, right? We want abstractions, and we want them to be self-contained. In this case, we want it to be, say, like reusable and predictable. And obviously, in the real world, especially like with remote targets and where there's non-determinism and there's other actors interacting with the service we want to exploit. It's never quite this clean, but this is the idea. Okay, so for heap-based buffer overflows, this manipulation process is typically done obviously on the heap layout itself. And it's usually a fairly labor-intensive task. So the analyst needs to understand the allocator, the manner in which the application uses the allocator, and then you also, given a starting state, you need to utilize the application's API in order to carefully craft the heap state, because typically you can't interact directly with the allocator itself. And this is what we're going to talk about automating today. So in reality, instead of having like this kind of nice, small heap state where we have 3 or 4 chunks, we end up having vastly more complicated things. So this is a visualization of the evolution of the program's heap over time. The x-axis is time, the y-axis is the program's memory space starting from lower addresses to higher addresses. So what we can see is as the application is initialized, we're getting chunks allocated one after the other. The green chunks represent allocated memory, the gray ones represent previously allocated but now freed memory, and the height of a rectangle represents the amount of memory in a particular chunk. So what we can see is we have hundreds of allocated chunks, hundreds of free chunks, they're all interspersed with each other, and it's we can't just eyeball the heap state and say, oh, we need to make, say, 3 allocations and like 2 frees, and then we're going to end up in the desired end state. So it is more complicated than the previous example in reality. All right, so just to formally define what we're going to be doing, we're going to have a source buffer, which is the buffer from which the overflow or underflow is going to, say, flow out of, a destination buffer, which is the thing we want to corrupt, and the heap layout optimization problem is we're trying to minimize this objective function, which is the absolute distance between the source and the destination. Obviously, you could have different objective functions because sometimes the data you're corrupting is okay, and sometimes it's not. Say if you're flowing into an unmapped page, that's obviously worse than if you're flowing just over application data. But the search that we're going to perform is we're searching for a sequence of inputs that minimize this function. So a sequence of inputs to the program to put the overflow source adjacent to the overflow destination. Okay. There are a couple of restrictions for this particular talk, and if you want to talk about alleviating these, come see me after. So first of all, we're going to assume a deterministic setting to begin with. The allocator's behavior itself must be deterministic. That's not a huge restriction because there aren't too many allocators that use non-determinism internally on purpose. The attacker must be able to set the heap into a known starting state or reset it, so via killing the target or something like that. And we are also assuming that in this particular case, there's no other actors interacting with the heap. So there's no other entity also triggering allocations and frees. And we're also talking about physical layout, not logical layout. And logical layout would be relevant if we're talking about, say, use after freeze and that sort of thing. Okay, so we need to solve 3 things. First of all, we need to discover how to interact with the allocator via the application's API, because, as I said, applications typically don't allow you to do that on purpose or directly or in a convenient fashion. We want to automatically discover how to allocate interesting data on the heap, so a corruption target, ideally. And then we need to automatically figure out how to place the source buffer adjacent to the thing we want to corrupt using what we discovered in the first 2 steps. Alrighty. So there are a few challenges with this, obviously. First of all, allocators don't provide an API which allows you to specify positioning. You can't say, put this thing adjacent to that thing, because in the context of a normal allocator usage, that makes no sense. Allocators themselves are designed to optimize different measures of success. In other words, they use vastly different data structures and algorithms internally. So if you have a solution for one allocator, it's not necessarily going to work for another allocator. Applications themselves typically don't expose a direct API to the allocator, so you need to figure out how to go through the application's API to interact with the allocator. Interaction sequences, which you can discover from the allocator, or sorry, from the application, typically have noise in them. So in some situations you get lucky and you can inadvertently trigger like a single malloc or a single free via the application's API. But a lot of the time what ends up happening is you can trigger the allocation you want to trigger, and then you also trigger like, say, 27 other allocations that may or may not mess with the heap state that you're working with. And then finally, the search space, if you were to exhaustively process all combinations of interactions, is obviously astronomically large, so we need to find some way of dealing with that. Okay, so as I mentioned, allocators have vastly different design strategies, and they use vastly different data structures and algorithms. And there are a number of different design decisions that an allocator developer can make, which can make the process of laying out a heap more or less difficult. So there are a few here which I've listed that are significant, some that are less significant. I'm not going to go into any of these except for one, because it is by far the dominant factor in determining the difficulty of this type of problem. And that is whether or not an allocator uses segregated storage. So if you're familiar with allocator design, then you can switch off for the next minute or two. If you're not, segregated storage is a allocator policy where you, first of all, when you receive an allocation request for a particular size, you allocate, say, multiple pages, and then you subdivide those pages into chunks of the exact same size, and you use those chunks to service future requests for the same size. And the key point is these chunks are never split again. They're never internally coalesced, so they're never internally joined together to form a bigger chunk, and they're only externally coalesced as a whole, so you can only ever free all of them at once. The key point here in terms of manipulating a heap state into a desired layout is that except for the first and the last chunks, all other chunks in the run of pages are adjacent to chunks of the same size. So if you see here in this example, we have a whole bunch of chunks in size 16 in segregated storage, and then a whole bunch of chunks in size 32 in segregated storage. And if we need to get a chunk of size 16 adjacent to a chunk of size 32, it can only be the first and last chunks here. So we need to figure out how to do layout manipulation at the scope of the runs of pages rather than just the individual chunks themselves. So this is an example of if we take 100 or so allocations and frees of different sizes. So there are 3 different sizes being allocated and freed here. Again, x-axis is time, y-axis is the address space of the target program, and the height of a rectangle gives you the size of a chunk. So you can see here is we have bigger and smaller chunks interspersed with adjacent to each other. This is non-segregated storage, so the application is putting chunks of different sizes next to each other, and if we need a chunk of the big size next to the smaller size, everything is fine, we can do that. However, if we then take that exact same sequence of interactions and we replay it on top of an allocator with segregated storage, what we see is we get three distinct mapped locations in memory, all of which only contain chunks of the same size adjacent to each other. So now we have a problem. If we need to get chunks of, say, the bottom size next to chunks of the bigger size, we need to fill all of that space between those two areas, and eventually we'll get the topmost chunk of the bottom size allocated adjacent to the bottommost chunk of the middle size. So segregated storage is a pretty significant a factor in determining the difficulty of these types of problems. Okay, so as mentioned, these 3 things are usually performed manually. So figuring out how to allocate something interesting on the heap to corrupt, figuring out how to interact with the heap via the allocator's API, and then given a starting state, figure out how to use the program's API to put the thing we want to corrupt next to the thing that we can flow out of. So let's, to begin with, assume that we have the solution for the first 2 problems, and we know how to interact with the heap. Could we design a search algorithm which can minimize the distance between the source and destination? Because if we can't do that, then there's no point in solving the first 2 problems to begin with. So ideally, we'd like the search algorithm to be black box. We don't have to customize it to the internals of every new allocator we come across or every new version of an allocator. And we also don't really want to be adding new APIs to the allocator or that sort of thing. So ideally, what we want is something which only observes the allocator in the sense of return values that comes from malloc, free, calloc, and realloc, and then OS generic things like, say, what pages are mapped and that sort of thing. And if we can do that, then we can work with any allocator effectively. The other design consideration that's worth considering is that random search might actually be feasible. So random search in this sense is you just have a random walk through the solution space. You're not learning anything between instances. It's effectively a brute force search. And you remember a while ago I said that the search space is astronomical? Well, it turns out there's actually a huge amount of symmetry in the search space because we typically don't care about the absolute positioning of things. We only care about the relative positioning of things. So if we have a source and destination buffer, we don't care where they're absolutely positioned in memory. We just care that they're adjacent to each other. Similarly, if we need to create holes in memory in order to capture noisy allocations, we don't care where those holes are specifically located in memory, we just care that they exist or not. So there is a huge amount of symmetry, as I said, in the solution space for this particular problem. Okay, so the next few slides I'm going to go over what the search algorithm actually looks like at a high level. For some reason I thought this would be a great way to display the actual algorithm itself, but I'll walk you through it. Effectively, the key point here is all we're doing is we are randomly creating instances. An instance is a solution. We're then providing that solution to the program, and we're getting back the distance between the source and the destination. If the distance is less than our previous best result, we say this is our new best result, and we move on. Key point, we're not learning anything between solutions. The construct instance function then is, again, it's another random function which constructs solutions via randomly deciding on this line here how long the solution is going to be, and then randomly deciding whether it wants to do an allocation or a free until it gets to the end of the solution construction, then returns it. Again, key point here, everything in this is purely random. We're learning nothing between solutions. Okay, so in order to evaluate this, we did two things. The first is constructed a collection of synthetic benchmarks, and then later we're going to talk about doing this on real programs. But just to see if the algorithm itself, so random search applied to mainstream allocators, can actually solve this positioning problem, we generated a bunch of synthetic examples. So the problem we're trying to solve here is, given a source buffer of size X and a destination buffer of size Y, can we randomly generate a sequence of inputs to the target program which place the source and destination immediately adjacent to each other? For the source and destination sizes, they're the cross product of these sizes here. And in order to initialize the application into kind of a realistic starting state, we captured the starting states of Ruby, PHP, and Python, well, two different versions of PHP. So the final experimental, I guess, configuration thing worth noting is this concept of noise. So we are obviously, because these are synthetic experiments, we're deciding what interactions are available for the search algorithm with the allocator. And the easiest case is obviously the search algorithm can interact directly with the allocator's API, and it can trigger exactly what it wants, and it can free exactly what it wants. As I mentioned, a lot of the time in reality, these interaction sequences are actually noisy. So what we're going to see in the results in a few minutes is there are experiments where there's no noise, there's experiments where there's one noisy allocation, there's experiments where there are four noisy allocations. Those noisy allocations are simply extra allocations that are added into the interaction sequences, such that when the search interacts with the allocator, it can't interact with it just kind of with a single atomic allocation or free. Okay, so what we're going to go through here is the solutions for running the search algorithm on dlmalloc, tcmalloc, and something called AVR libc, which is a drop-in libc replacement for embedded systems. There are a couple of things worth explaining, first of all, namely the headers on this table. The allocator is obviously the allocator that the search algorithm is interacting with. The noise is the number of noisy allocations. The UND and OVF are the results for overflow experiments and underflow experiments, because it turns out one of those cases tends to be easier than the other for reasons I'll go into later. An optimal layout is where the source and destination are placed immediately adjacent to each other. So that's these two columns here. These two columns here represent the percentage of solutions where the source and destination were within a page of each other. So that's also worth making note of, because even if we can't get the source and destination immediately adjacent to each other, if we can get them within a page of each other, we know we at least won't trigger a page fault if we trigger the overflow or the underflow. And then finally, the average underflow error and average overflow error is a representation of the amount of actual error for situations where we didn't actually get the two things adjacent to each other. So what we did is, for each combination of allocation and destination size, starting state for the heap, and a number of noise, we ran 500,000 instances. In other words, we generated 500,000 candidate solutions, and these are the results from those. So what we can see is for AVR libc and dlmalloc, which both don't use segregated storage, we could solve almost all of the instances using random search, which is worth knowing. We then add tcmalloc. So tcmalloc is a segregated storage-based allocator, And what you can see is, even with no noise, first of all, we get a drop in the number of optimal solutions achieved. So we can see, obviously, that segregated storage has this impact. Then once we add noise, we can see here, we get a drop from previously, say, DL malloc, we were solving 97% of the instances, down to 22 in this case. And the others are hovering around 50%. So what this means is that in around 50% of the solutions, we're getting the source and destination immediately adjacent to each other. But one thing worth noting is that the average error is still quite low. So the average error here is a representation of, for the solutions that weren't optimal, how close they were together. So again, it's still less than, say, one allocation that we're off by, effectively. And then finally, we add 4 noisy allocations, and we see that the results drop again. So the takeaway from this, effectively, is that if we have no noise and non-segregated storage, then random search works pretty much fine. Within less than 15 seconds, most of these instances were solved. As we increase noise and as we add segregated storage, random search starts to struggle a bit, but the average error is still relatively low. So we're still getting these source and destination buffers pretty close to each other. So the kind of takeaway from this is that while the random search approach isn't perfect as the problems get harder, it is good enough that it was worth our while implementing a real-world system and actually trying to apply this to real bugs. Okay, so the random search, like I said, looks promising. If we want to actually do this on a real target, we need a few different things. We need to figure out how to trigger different allocator interaction sequences via the target's API. We need some way to discover how to allocate interesting target data on the heap, and we need an implementation of a search for that real program. So for this, I decided to use PHP as the evaluation system. So PHP is pretty large, it's fairly modern, it's written in C, it is a non-trivial interface for interacting with its heap, in other words, programs written in PHP. And what our tool is going to be doing is effectively writing PHP programs that manipulate the target state, in other words, the PHP allocator, and then trigger some vulnerability. And when the vulnerability is triggered, its goal is going to be to put the source and destination adjacent to each other such that the destination is corrupted. So the system itself looks something like this. So we have 3 distinct phases. We have interaction sequence discovery, where we try to figure out how to interact with the program's heap. We have corruption target discovery, where we try and automatically figure out something interesting to corrupt. And then we have a vulnerability template, which kind of describes how to put these 2 things together in the context of a random search to produce what we're calling a primitive skeleton. How are we for time? Good. Okay, so those of you that are familiar with, I guess, exploitation terminology, a primitive is like a fairly well-known thing. The skeleton in this case is worth clarifying, though. So the output of the system is a PHP program which guarantees the relative positioning of the source of the overflow or the underflow and the destination. It doesn't, however, guarantee that the vulnerability will actually corrupt the destination, because it doesn't reason about the vulnerability itself, it only reasons about positioning. So it's up to the user to ensure that if we're saying, or if the system says, I can get you this source buffer within 8 bytes of this destination buffer, you as the exploit developer need to make sure that the vulnerability will actually corrupt 8 bytes and then corrupt the target. And then finally, it doesn't discover how to use the corrupted data. So it will guarantee positioning, and then if you ensure that the vulnerability actually performs the correct corruption, it will guarantee that you get the destination corrupted, but it ends up to you as the end user to figure out how to use that corrupted data. So these are kind of, I guess, future work. Okay, so what we need to do is we need to figure out how do we actually programmatically interact with the heap that's being used by PHP via the API presented by PHP, which is PHP programs. So what we want to do is we want to synthesize fragments of PHP code that trigger unique interaction sequences of the allocator. This is based on work I presented a few years ago at Infiltrate. What we're effectively going to do is we're going to take all of PHP's regression tests and we're going to parse them down into minimal fragments, and then for each of those fragments, we're going to record the interactions that fragment triggers with the allocator. And then we're going to start fuzzing the fragments, recombining them to build bigger and more complex chunks of PHP, which have unique interactions with the allocator. So effectively what we're doing is we're fuzzing, but with a minor twist. So normally when you're fuzzing, say, fragments of PHP or JavaScript or whatever, you're using values that you're hoping to hit edge cases, right? So 2 to the 32 minus 1, 0, or so on and so forth. In this case, what we're going to do is we're going to replace integer values and strings with lengths that we haven't seen before in terms of an allocation size. So if we haven't seen an allocation of size 256, then we're going to start spraying the value 256 into different chunks of PHP code in the hope that it results in an allocation of that size. Secondly, our measure of fitness isn't based on code coverage, because that's what we don't care about. It's based on whether or not we trigger a new allocator interaction. If by chance we find a bug and we actually cause the allocator to crash, we throw that away because we don't want that to happen. We want to find new allocator interaction sequences. And then we favor the shortest, least complex fragments during this fuzzing. So if we take, this is a test from PHP, we take this to begin with and we break it down into the function calls contained within it. So each of those function calls takes a number of arguments, and we then abstract that slightly further up to something that looks like this. So we break it down into, we have the function calls and we have the associated types of the arguments that it took. Then we pass this into our fuzzer, and what the fuzzer does is it randomly selects one of these, it looks at its argument types, then it randomly selects a value for those argument types. So you end up getting something like this. So here, say we pick the image create true color, we know it takes 2 integer arguments, and then we start fuzzing the final argument to find new interaction sequences. Or similarly, if we have this image convolution function, we can see it can take different argument combinations. And effectively all we're doing is we're taking little fragments of PHP, we're recombining them, and then we're using instrumentation in order to determine what type of allocation sequences they trigger in the allocator itself. So PHP comes with about 12,000 tests. From those 12,000 tests, we can get, say, 300 standalone fragments, which are like these individual function calls. And then fuzzing those for like 15, 20 minutes, you end up with tens of thousands of different allocator interactions that you can trigger. So the output of this is effectively, we now know how to interact with PHP's allocator using its API. That's what we wanted. And the search now, instead of, say, being at like an alloc-free level, what it does when it constructs instances is it pieces together these fragments of PHP code in order to generate a sequence of interactions with the allocator. And the search is now a search over the space of PHP programs for a program that minimizes the distance between the source and destination. Okay, so that was the first step. The second step, which we could optionally automate, we don't have to, is finding interesting corruption targets. So sometimes the exploit developer themselves will already know this is the thing I want to corrupt, therefore they know how to allocate it. But for the sake of adding a little more automation, we can also try and figure out what are interesting things to corrupt on the heap and how do we allocate them. So there are program-specific things, so you could like permission bits and that sort of thing, but in our case we're going to focus on our pointers. So what we want to do is we want to have another search which figures out how to allocate pointers on the heap, which can then be used as part of our positioning problem in order to, say, build a read or a write primitive. So as before, we take the fragments of PHP as input, we execute each of them in isolation, and after the fragment, or as the fragment is executing, we record every dynamically allocated object. Then when the fragment terminates, we record the objects that are still live, and we search over the actual memory used by that object, looking for things that look like pointers, which we can do based on heuristics, so their alignment, the value they have, the mapped address space of the target process, that sort of thing. So this is pretty straightforward. So at this point what we have is we have something that can construct PHP programs which randomly manipulate the heap. We have something which can tell us what fragments of PHP code will allocate interesting targets on the heap. And what we want to do now is we want to put these things together to perform the actual search itself. So each vulnerability we come across is obviously going to have a different kind of setup. It's going to require a different API to trigger. So rather than hard coding vulnerability-specific information into the search space itself, what we do is we have these vulnerability templates, which the search will fill in. So what they look like is as follows. So this is from a PHP bug report. It triggers some overflow in the second function here. So what we will do is we will take whatever our vulnerability trigger is, and we will construct a template that looks like this. So the template has a prelude, which is just some things that need to happen. It then has something for creating the destination, which is the thing we're going to want to corrupt, and then finally it has a vulnerability trigger. And the system is free to insert heap manipulation, or it's free to perform its search at any location outside these tags. So it can insert code here to do heap manipulation, or here. So this is what a vulnerability template looks like. It's very straightforward, and the overhead for the users is pretty low. Alrighty, so this is what we spoke about before. We have interaction sequence discovery, which is just fuzzing PHP programs for new allocator interactions, corruption target discovery, which we just spoke about, and then we have a vulnerability template. We put all these together in the search, and what we get out are things that look like this. So they're valid PHP programs that they have the prelude from the template. Then here we can see a bunch of functions that have been randomly selected and assembled together because they have some useful interaction with the allocator. So here we can see that the system has discovered that the image create true color function and the string repeat function obviously do interesting things in terms of allocating things on the heap. It's also figured out that it can trigger freeze via just destroying objects like this. And then the rest of it is just from the vulnerability template. So these are the instances that are going to be created during the search, and we're going to randomly create thousands, hundreds of thousands, billions of these until we find one combination of these function calls, which places the thing that we want to corrupt next to the thing that we are flowing out of. Okay, so this is kind of the end-to-end process. We start off with a vulnerability trigger. We can create from that a template, and then the system creates these instances. Okay, so the evaluation for this was based on 3 CVEs from PHP's bug tracker. If you're wondering how I picked these, I effectively went to the bug tracker and started looking for linear overflows, and these were the first 3 that I came across. There's no purposely hard cases left out. It wasn't the case that I found 100 and these were the only 3 it worked on. These were the first 3 that I came across. So just to explain some of the headers here, the source size is the size of the buffer which is being overflowed out of when these 3 vulnerabilities are triggered. The destination size is the size of the object that we want to corrupt. Noise is a count of the number of allocations which are triggered when we allocate the overflow source that are not the source buffer itself. In other words, these are other allocations which can mess up our heap state, as I mentioned before. The initial distance is the distance between the source and the destination if we simply take the trigger as provided in the bug report, add our code to allocate the destination and simply run it. So we can see here by default there's quite a large distance between the source and destination. Obviously, if we had a trigger which already put the source and destination immediately next to each other, then the search would just be wasting our time. And the final distance is the distance that the system was able to get the source and destination to be from each other. So we can see in 2 of the cases it achieved a perfect result, and in the final case it was off by 16 bytes. So there was 16 bytes between the source and destination. There are a few things I guess worth noting here. The first is you can see in the cases where we have a lot of noise that the time to the best instance is obviously far higher than the case where we have no noise. Again, we saw this in the synthetic evaluation as well. In cases where we had no noise at all, we could solve the problem almost instantly. And we can also see here in the final case, we didn't actually get a perfect result. The reason for in this particular case, when I looked into it, was there's 2 allocations of size 8 which take place as part of this noise here, and the system wasn't able to figure out how to get them out of the way, basically. But overall, it works pretty well on these evaluation instances. Okay. So there are a few takeaways from this that I think are worth mentioning or reinforcing. First, so black box random search does appear to be an effective mechanism for automatic heap layout manipulation. There are a number of instances that were clearly hard that it couldn't solve, and if you want to talk about how ways to solve those, find me later. Segregated storage was clearly by far the biggest differentiator between hard and easy instances. With dlmalloc, with AVR libc, and no noise, black box random search can solve these instances in like fractions of a second. And as noise increases, obviously the difficulty of the problems also appear to increase. So there are a bunch of things that we can do to improve this. The search algorithm itself, we can clearly improve. We're learning nothing between instances at the moment. At the moment, I'm working on basically a fuzzing /GA type approach, which I can talk about if you find me later. The determinism restriction is obviously quite a harsh restriction that would be worth alleviating. And also, it would be very good to see this ported to other things, so media players and JavaScript engines, document viewers, and that sort of thing. Alrighty, so the paper and the code you can find there. The paper that's up there at the moment is like kind of a technical report. If you want the full research paper, just send me an email and I'll send it on to you. Or you can just send me an email with any questions you might have. Other than that, I am finished. That's it. Any questions? Yep.
Where are you?
Okay.
Come see.
That's a very interesting presentation. So I've worked with a number of the allocators that you specified there. One of the problems I've seen in the past is when you start considering threading issues.
Yep.
And the effects of effectively the instrumentation.
Yep.
What mitigations do you take to get the instrumentation not to be a problem?
So there is no instrumentation. That was this is something I wanted to avoid, basically. As soon as you start adding instrumentation, the heap layout gets messed up, and then the test case that you have looks nothing like the real case. So because it's done in a completely black box fashion, the only observation I'm doing of the allocator is simply looking at the return values that are given back from allocate, free, realloc, calloc, those sort of things.
So we're using something like a preload approach or interposition on those allocators, or were you replacing the allocators themselves, or just passing through?
Just passing through. Cool. Any other questions? Nope. All right. You're free. Thanks.